Tactum brand breaker, UK English system. As you can see, it says, then push this forward. Contactum England. These basically have a nice little green when they're off, red when they're on, and side of it has a hole there so you can pin these two together. If you want to take off three phases, just has a pin across. This side goes into the bus bar, or they put in a piste jumper, a live, so screws there, carry that down, right? DIN rail system, so basically a rail that has a tapered edge, and to get this to stay, you just press this in like that, and it locks, and then use a screwdriver on that side there, and you push it out, comes out. Obviously this is burnt. Most likely it's because the connection was loose, arcing, and heat. So obviously this is dead. These two are fused together. This one may not be damaged, but no one's going to use back that. That's a really bad idea. On this side, there's a little diagram that shows how to use a screwdriver. There's also distances, a little bit written down there. 2.5 Newton meters max. And not quite sure what these are. Haven't really looked that up. So, a couple little brass rivets holding them together. So first thing I'm going to do is separate these. I don't think it's really very much welded together. It's just a little bit of plastic there, so I suspect you can separate it easily. And then open it. As far as I understand, breakers have two different systems. This is a B32 breaker. If you look on top, you'll see B32. That B32 means it's a B-type breaker, 32 amp, 230 volts to 400, IEC-EN, right, designations, manufacturer's number. B-type breakers, well, that's a whole topic for itself, but basically you have A, B, C, D. A would basically have, I think it's 1 to 2 times the current, B 2 to 5, C 5 to 10, and D would be, I think, 10 to 20 times it is. I'll check that up, and if I'm wrong about that, I'll stick something, a note down in the bottom. Essentially, this 32 amp breaker, let's just say it was a 10 amp to make life easy. A 10 amp breaker will not trip at 10 amps instantaneous. Continuous current will cause a heating element in here. So there's two independent trips. A heating element trip, which after 10 amps, over a period of time, it will trip. If that was a 10 amp breaker, let's say it's 12 amps, it would trip, but it will take a period of time for the heat to build up, and that is given in tables. If it, however, has an instantaneous short, a 10 amp breaker, if it's B-type, will be between 20 and 50 amps before it trips. If it's a C-type, it'll be between 50 and 100 times before it trips, 100 amps. And this is because instantaneously, when you put on something like a motor, you get a high inrush current. So you don't want something tripping instantaneous high current. What you want it to trip at is a continuous overcurrent, which of course wires the heat up. This is supposed to heat up faster than trip. Or secondly, if you have a short, and then you determine that short by the instantaneous current that runs. So if you have a device that pulls out the current like a motor, you want it to have a higher rating, so it's going to be a C or a D type breaker. That gets complex in explaining how you determine whether it makes sense to use a C or D type breaker. That's a topic for a whole other discussion, because if your inductance is too high in the circuit, certain breakers will not trip actually instantaneously. So let's open it up, let's have a look and see if you can find the two mechanisms, the instantaneous trip and the thermal trip. Okay. It all fell apart as soon as I tried to pull it. Two springs came out, no good. But as we can clearly see here, this is a lug for basically plugging on the bus bar. It comes down here, it's resistant welded to a piece of copper, and there's this mechanism here which I have not been able to figure out yet. This moves forward and touches here, which engages. When you pull this board, that moves, changes the color, and moves this across here. So that's fine, that makes sense. That contact, there's a pigtail, resistance welded, goes into inductive coil and comes back out, comes down here and joins to the output. Essentially, once you have high enough current, the force created by this inductor essentially solenoid will pull this pin, disconnect that, break the circuit. So that makes sense. That's your instantaneous strip. And depending on how many coils, how this is set up, you'll get the force configuration correct to be able to disconnect. That makes quite a bit of sense. What I have not been able to figure out yet, all of this mechanism, it's a bit, fickle, easy to destroy apparently. But yeah, mechanism allows you to snap a breaker in easily, but well, takes a lot of force to snap it in. Let's just show the next one. That's how easy it is. It's more difficult to put in, but there's a little bit of force and it snaps back out. So all that mechanism, I assume they deem necessary. I haven't looked at the exacts of it. There's probably multiple ways to design this. This we'll look at and try to figure out. And then there is this weird little thing, that there. Not sure why that happens. That, if you look at it, is somewhere right here. That is a little piece of plastic with a piece of metal below. But the plastic insulates that metal from contact. If we flip this over and we look at the line, that ends up right about here. So I don't know how that plastic blocks that piece of metal and what that does for the heating. I can't quite figure it out. I mean, is this a bimetallic? But it's not a bimetallic strip, so it's just a copper piece onto this. And then let's have a look at this so you can see. Look at this. This is, I don't think it's aluminum. Looks like steel. Steel pieces held together with what appears to be some kind of, well, paper impregnated. Doesn't appear to be fiberglass, but what would be the purpose of this apart from quenching an arc? That would be my first interpretation of something like this. It's for arc quenching, but how does that quench an arc when the arc would occur at a disconnect here? How on earth does that quench an arc? Does this provide an alternate path? Is that what this is about? Maybe that's what I'm, guess could be. You have a connection here, you have an alternate path, so you have the quenching of an arc when it comes across. I don't see it. I don't think it makes sense. This does not connect to that. It shouldn't, obviously, because then it'll bypass the whole, defeat the purpose of this thing. So I don't understand what this is for. And I don't see what the thermal is. And I don't catch what that piece of metal idea is doing. There's also one final thing which I'm not quite sure about. I'm going to disassemble everything inside and see if I can figure out. This. There's this little button type thing here. Screw that adjusts this. And I'm not sure why we need it. I'm not sure that this is required for calibration, maybe later on. Just to push this in or out a little bit more, or just to tighten it in position. I'm not sure why. Maybe just a little bit of calibration just to get this correct, because this looks a little fickle. It looks like you can't really accurately predict. And again, that's why probably the ranges exist, 5 to 10, because, well, maybe we can't exactly get it 5 or exactly get it 10, but we know it will fall somewhere in between. So let me just disassemble a bit more and see if I can figure out anything. Probably not, but let's see what we can do. It's quite a number of pieces, like 52 pieces. Plastic, you have this little clip, these two complex molded pieces, these two small pieces, this one, this is pretty complex, that one and that one, and then the housing for the relay. So that's solenoid, sorry. That's probably 10 pieces there. 1, 2, 3, 4 springs, 3 pieces of steel. This is a combined piece, not sure what it does, as I said. Then there's 5 pins, right? 4 linear and 1 curved. This piece is a compound piece, is 1, 2, 3, 4, 5, 6, 7, 8, 9 in there. And then the overall coating, 6 brass rivets. The solenoid has this, this and this in it, right? There's this piece, then there's this metal piece, right, with no special contact, as opposed to the other side having a special contact, which is this side here, right? Pigtail, coil that is not exactly circular, it's fairly flattened steel and rolled around that way, so pretty much very sturdy. And next pigtail, this piece of steel, which welds on to this piece here, then goes a separate piece here. This is one piece, and then there's a bolt there, right? Screw, let's call it. There's this piece of copper, which is then resistance welded to here. There's a small pad for arcing and a special material, I would assume. Then of course this lug, which comprises of two pieces. Fairly complex device. This is brilliant. It is expensive to make. I understand now why these things cost that much. I want you to note of this. These levers, they come in different colors for different wattage amperages. It's something unique I've seen on the English system, not something you see on the American system at all. So this brown will be a 32. So once you see a brown, you know it's a 32 amp breaker. You online and shows yes, this is indeed for arc quenching. Made sense. It's the only thing that really made sense when you do this kind of arrangement and dissipation of the heat. And I am guessing this here is the bimetallic strip for the thermal trip, because I can't see anywhere else that we have the thermal trip. It normally is a bimetallic strip, and this seems to fit the bill. I'm not sure why they have this piece, but this piece on the bottom here looks flexible, so it allows the bimetallic strip to move. But it appears that this is the bimetallic strip, and that will probably push also on the back of the plunger, which was essentially this piece here, the back of the plunger, and have the same effect as if the plunger had basically pulled in. So essentially that would have pushed, or the plunger would have pulled in that way. Either which way, it would have caused a trip. So this has to be the bimetallic strip, and this is the overload. When it's significantly overloaded, the high current.